Good morning, good afternoon, and good evening to all the distinguished guests joining us from different time zones. A very warm welcome to the International Conference on Computation Research and Data Analytics ICCRDA 2025. I am Dipanshi Agarwal and I'm honored to be your host today. ICCRDA 2025 is organized with the objective of bringing together innovative scientists, professors, research scholars, students, and industrial experts in the field of science, computational methods, and techniques to a common platform. The primary goal of the conference is to promote the exchange of innovative scientific information between researchers, developers, engineers, students, and practitioners. Overall, the conference will provide the researchers and attendees with prospects for national and international collaboration and networking among universities and institutions from India and abroad for promoting research. ICCRDA 2025 will be organized by DuyTan University, Vietnam on 17th and 18th January 2025. The day featured two keynote talks. First, Dr. Surbhi Bhatia Khan. Second, Dr. Rishabh Singh. The presentations and keynote address set a dynamic tone to the conference, sparking insightful discussions and knowledge sharing. Moving on further with the introduction and welcome address by Dr. Deepak Gupta, Organizing Secretary, ICCRDA 2025. I invite you, sir.
Thank you so much, Dipanshi. Good morning, good afternoon, good evening to all the participants of ICCRDA 2025 around the globe. We have already started the paper presentation in ICCRDA in online mode. We have around 77 papers has been presented today. On behalf of the organizing committee of ICCRDA 2025, I welcome you all the delegates, participants to the second international conference on computational research and data analytics, being organized by DuyTan University, Vietnam, publication partner IEEE. On behalf of organizing committee of ICCRDA 2025, I extend my heartfelt gratitude to the governing management, faculties, staff, and students of DuyTan University, Vietnam, the keynote speakers, our panelists, delegates, session chairs, paper presenters, and participants of this conference. First of all, I would like to thank Professor Bao Newson, Professor Nu, and Dr. Dang from DuyTan University, who helped to organize the conference in such a successful manner. I would like to welcome our keynote speaker, Dr. Surbhi Bhatia Khan from University of Salford, UK, Dr. Rishabh Singh from IIT Patna. We are grateful to them for accepting the invitation to take part in ICCRDA 2025 and will share their expertise and knowledge with the participants of this conference. We are grateful to our core organizing committee chair who have not present here, but have supported us during the organization and implementation of this conference, our general chair, Professor Joel Rodrigues and Professor Abol Ella Hassanan. Now, I would like to give some insights regarding the ICCRDA 2025. ICCRDA 2025 is in its second version and have attracted more than 500 papers. And after rigorous peer review process, only 77 papers has been accepted for presentation with an acceptance rate of only 15%. This conference will not be possible without the active participation and support of Dr. Ankit Vidyarthi and Dr. Aditya Khamparia. I would like to appreciate them for giving their time and energy in making this event a huge success. At last, but not the least, I would like to thank our sponsor, student volunteers, reviewers, special session organizers, participants, keynote speakers, and publication partner for their constant support in organizing this conference in hybrid mode. Thank you so much.
Thank you so much, sir. Our first keynote speaker, Dr. Surbhi Bhatia Khan, University of Salford, UK. Surbhi Bhatia Khan is an assistant professor in the School of Science, Engineering and Environment, Data Science Department at the University of Salford, United Kingdom. She is project management professional certified from PMP, USA. She is ranked among the top 2% scientists globally for the second year in a row, 2023 and 24. As acknowledged by Stanford University and elsewhere. She is supervising and co-supervising a number of PhDs and research associates. She has published over 200 articles and books in high-indexed outlets with her students and colleagues. She has been awarded with the Best Paper Award and several other recognitions. She is also serving as associate and guest editor in reputed journals. She is working on some projects in external funding from UK, India, and Middle Eastern institutes. She has been serving as session chair in many IEEE conferences, been invited as a resource person at international conferences and FDPs, and has enjoyed honorary positions by advising universities to achieve research and teaching excellence. She is also a member in Women in Data Science Ambassador 2024. Her research interests are machine learning, deep learning, data science in healthcare, sentimental analysis. I invite you, ma'am. Dr. Surbik
Yeah,
Bhatia Khan.
hi. Thank you so much, Dipanshi, for the brief introduction. Thank you, Dr. Deepa Gupta and Dr. Ankit, for inviting me to the for the keynote in this conference. And it's really early morning from UK. So anyhow, can I share my screen now? I'm not able to share my screen. Sorry.
Vineet, can you check?
Ma'am, kindly press the button of share screen.
Yeah, I'm doing that. But okay, now yes, I've got the access. Thanks. Yeah, my screen is visible.
Yes, ma'am, it is.
Right. So I'll be presenting a short talk on deep learning framework for automated brain tumor diagnosis, classification, detection using multimodal imaging. Brain tumors. Now, these brain tumors can disrupt the central nervous system. We all know about it, and it's the most critical conditions which actually affect this nervous system, and they may have they may vary widely in size, type, or you can say they can impact the bodily functions depending on the location where they are found. So the complexity of this brain tumors basically makes the early diagnosis or the treatment particularly challenging. And uh, we need some form of early detection which can actually enhance the possibility for some successful treatment using different techniques. Yeah, excuse me.
Ma'am, maybe it was some kind of disturbance. You can continue.
All right. Is it okay?
Yes, ma'am.
Right. So we are talking about the complexity of these brain tumors, as these are very important, and particularly they are very challenging as well. So early detection can significant enhance the possibility for some kind of successful treatment, which we are looking through different techniques such as AI uh, AI methods. Now, how the deep learning, or we can say the role of deep learning, has is there in medical imaging. So, deep learning has emerged actually as a very uh, powerful tool because it offers substantial improvements over some form of traditional methods. Now, we have different kinds of sophisticated algorithms that can actually identify to learn the patterns uh, or certain kind of anomalies that we have, and then it can also reduce the potential for human errors, and which could give a kind of a correct diagnostics or early detection, and we can consider them more consistent and more reliable. So if we see the revolutionization which has happened in deep learning, so integration of this deep learning and medical imaging for this brain tumor represents kind of a highly pivotal advancement in healthcare technology or the healthcare sector, because it allows I mean some form of analysis wherein we can combine multimodal imaging data, which will give us more informed, accurate medical diagnostics. Now, what are the different revolutionizations that can be discussed with this deep learning uh, in the field of medical imaging, because of some kind of advanced analysis, interpretations that we make, and the diagnosis. So, the first one, as you can see in the slide, is the image analysis and feature extraction. So, deep learning models, particularly, you can say CNN, convolutional neural networks, okay, they have excelled in extracting some meaningful information, or you can say some meaningful features from this medical images, and they don't need any kind of manual feature engineering tasks wherein we needed them before with the traditional techniques. So they have some hierarchical representations layer by layer of the image data, and they capture both low level and the high level features. So where they are particularly used, like in segmentation, classification, detection. Now segmentation is going to identify some specific regions like tumors or organs or tissues. Classification will be categorizing the medical images into some predefined classes, maybe like cancerous or non-cancerous. And detection would be locating some form of abnormalities where into some nodules, or you can say some particular region. For example, the version of our CNN, we have RCNN, right? We have faster RCNN. These are different versions. Now these are very much used for object detection in x-rays. So the second point says disease diagnosis and prognosis. Now what does this mean? Now deep learning also helps in diagnosing diseases by recognizing some patterns and abnormalities in imaging data. Now, these models can actually analyze large data sets to detect some variations that may be missed by human experts. And that is why deep learning is playing a revolutionizing role in medical imaging or the healthcare sector. Now, again, DL models, they are widely used for breast cancer detection, in mammograms, lung cancer, in CT scans, and then you have different other types of cancers in dermoscopy. So we have some form of neurological orders, which is again analyzing some MRI or the PET scans, uh, or some diagnosing some early signs of Alzheimer disease or some heart strokes. And then we have cardiovascular health, which is again detecting conditions like heart defects or some blockages which are there through some CT scans. So deep learning is also playing an important role by improving the quality and clarity of the images. So they do image reconstruction and they enhance the quality. So again, we have some techniques such as super resolution imaging, or we have some reconstruction, right, which are used in the healthcare sector using some deep learning based reconstruction techniques like automap, etc. We also do have the clinical decision support. So deep learning systems actually automate the repetitive tasks, right? So it will lessen the burden of the radiologists basically, or the clinicians, to focus on some complex cases. So we can do some prioritization, like identify some urgent cases and highlight them for some kind of immediate review from the doctors, or we can also help the radiologists using deep learning techniques to annotate which exactly part or I mean medical images more faster, you can say. And then again, combining the images coming from the image data coming from clinical and other genetic information will also help in decision making. So it actually gives a overview, kind of a workflow automation and the clinical decision support using DL. We also have got some predictive analytics here, wherein DL models are going to analyze patterns over time. What does it mean to predict disease progression or some kind of treatment outcomes, which is gonna again help in personalized healthcare. So like in predictive analytics, you can say we can estimate the survival rates or treatment efficiency based on the imaging biomarkers, or support, for example, radiotherapy to some person by specifically mapping those target areas. So deep learning has actually revolutionized the overall healthcare industry by several factors, which I have discussed right now in this slide. Coming to this image, you can very normally see that it's all about talking about multimodal imaging. Now, what is multimodal imaging? It basically refers to the use of multiple imaging techniques that we do have in hospitals. Why we have to capture detailed, or you can say some complementary views, some obstructed views of structures and functions within the body. Now, of course, these views is going to help in diagnosis, right? Or we can do some treatment planning, or they're going to bring some kind of outcomes. Now, what are the famous multimodal imaging that we have? We have the first one, you can say, is MRI. So how it works, it of course it's something related to magnetic resonance images. So it has a strong magnetic field or some form of radio waves, and they form some detailed images of the soft tissues. So where they can be used, they can be used for detecting tumors, they can be used for finding some inflammations or some neurological orders as well. The second one in queue is the CT, which is a computed tomography. Now, this CT scan, it uses some X-rays. Why? To capture some form of cross-sectional images of the body. Again, they can be reconstructed into 3D views, but the key features, you can say that they do fast imaging, or they are very effective for finding the fractures in the bones. So again, we can determine fractures, some cancers, or some internal bleeding with the CT scans. The next in the queue is the PET, which is generally used in cancer detection. So PET full form is position emission tomography. Now, this PET, again, they use some radioactive lasers which are injected into the body to visualize activity or some biochemical processes which are happening. Now, if you want to detect some changes in the cellular activity, often which is before the structural changes can occur, then we are going with the PET scan. And again, as I mentioned, they are used for finding out the stages in the cancer, or even for researching the disorders which are there in the Alzheimer disease. We do this PET scan. We do have ultrasound, and everybody knows about it, which is using some high frequency, what do you call, sound waves to create some real time images. And we also use hybrid imaging techniques like combining MRI with CT scan or PET with CT scan, to integrate the functional metabolic, you can say, imaging with some high resolution uh, tissues control. So we have all forms of multimodal imagings available, which actually will be used as the data set to further get applied for the training of the models using deep learnings. Now, what are the several applications of AI in imaging? The first one says, I've listed a very few, there are lot many. So the first one says the neurological disorders. Now, we know about it, that AI analyzes some form of scans, for example, brain scans, to detect early signs of diseases, right? For example, Parkinson's or epilepsy using some multimodal data. We have oncology. Now, multimodal AI can also integrate the two type of scans, which I just now discussed in the last slide, which says MRI and PET. Now, these can be combined together to distinguish between some form of benign or malignant tumors, you can say. Then we do have cardiology. So AI in cardiac imaging will identify, of course, some deposits or some what you call as heart defects as early heart diseases, heart risks. Uh, Now, the main question of research comes here that uh, how can we actually leverage these capabilities of deep learning when integrated with multimodal imaging techniques? And of course, we are doing this to enhance the predictor, the precision, or you can say the reliability of the tumor diagnosis. Now, uh, this question is going to address all the current limitations that we do have in diagnosis, and we can use some modern technology like AI, which can achieve better results or better prediction outcomes in medical imaging. So transformation is what we need. Now, uh, what can be the key objectives? So the first objective says that we need to develop a deep learning model that integrate multimodal imaging data. Now, this means that we need that can effectively basically process, or they can integrate data from different imaging sources, like maybe MRI, maybe CT, maybe PET. And this overall integration will help to find the unique strengths from each modality to provide a comprehensive understanding of the brain tumors. Uh, the second objective, it can be aimed to enhance or to improve the overall model performance by employing some advanced feature fusion techniques. Now, these techniques again are designed to extract uh, uh, some form of what you call some most distinguished or discriminative features from each imaging type, and then again it's going to help in overall models diagnostic accuracy. The object 3 can be used to create a robust classification system. Now, this should be enough robust to actually classify different types of brain tumors, right? Which is very, very important for determining the appropriate treatment strategies. So, this is what is the objective 3. Coming to the objective 4 is evaluating the model's effectiveness. So it needs to be validated with both clinical and the publicly available data sets. Why? To ensure that what we are working or what we are planning to get it integrated into the real time system is often is working correctly, it's robust, and it's applicable across different patient demographics, or you can say different clinical settings. Now, once we do that, we can plan to develop a user friendly interface that can either involve some clinicians or radiologists or some health practitioners to easily interact with the system, right? Again, it's going to mark the technology, right? Accessible and practicable to all the people which are you working in clinical use. So, coming to the review of literature that I had done, uh, we have some form of previous histories which says that convolutional neural networks and their role in enhancing the image analysis. So it reveals that significant progress has been made in the use of deep learning for medical imaging, particularly CNN, but still, I mean, we need to have some advancement of analysis, which is going to combine some complex imaging data and for more detailed or precision results. Now, integration of multimodal data, which combines again information coming from different scans, MRI, CT, etc., has again shown a comprehensive kind of diagnostic accuracy, which is giving a holistic view of the tumors. But again, we need more advanced techniques in this as well. The third says that we have some attention mechanisms, which is again a very, they have been a major development, which is focusing on model analysis, on the most relevant features. But again, enhancing the precision of tumor detection and classification is again needed. Now, despite of these advancements that we have seen in this slide, if you see the lower part of identifying the gaps, there are some issues. So one of the major issue is the limitation of the single modality imaging. Now, it fails to actually capture the complete uh, pathology of tumors. So that is what is missing. There's also significant need for models that is actually generalizing effectively, not working on a single part. So they can generalize over different populations because different patients has different demographics, and again, the different hospitals have different clinical settings. So many current models that are there have been made. They perform well under controlled conditions, but they struggle if the conditions are varied or there are more different clinical environments. So that is one of the, again, the second major issue. And the third one is the ability to process the data in real time. Now, it's very, very important that we can do that in clinical decision making, right? Because enhancing this would actually help to improve the practicality, or you can say the practical utility of deep learning systems, which we are discussing during some form of emergencies. Uh, Importance of addressing these gaps will actually be very, very important for the research and development, and improving these areas will actually not just enhance the effectiveness, but also they will help to practicalize, I mean, make the system more practical and reliable in the real world clinical settings. Now, this is a very simple methodology structure that I have just now, I'm just going to speak about it. Before speaking with the methodology part, I also want to tell you about the different data sets that are available for the brain tumor challenges. Like we have BRATS, which is available. It's a comprehensive data set focusing on the brain tumors. You can use for segmentation classification, available free. It has multimodal MRI scans. You do have the other data sets available on Kaggle. Then you do have the data sets like an open neuro. You do have some data sets on Alzheimer disease as well, which is available, like dementia bank data set, which you can get easily. It's an open source data set. You can get the data set from, as I mentioned, from Kaggle as well. So for doing your research or testing your models on these data sets, which are freely available. Coming to the methodology part, now the first step here, if you see the right hand side of the figure, we have input images. So data collection, when you have the some form of input images like coming from different sources, or MRI scans, for example, or combination of MRI or CT scans particularly. Now, that is the most important part as data collection. Now we have, as I mentioned, we have diverse range of imaging data, right, which can be again collected from public data sets. It can be coming from the clinical partners. So each of these imaging, it will provide some unique insights into the brain structures and then tumor characteristics. uh, the second step, as mentioned here, is data pre-processing. What does it mean? It means to clean the data. What does this mean? To remove noise, to select the task relevant features, right? So pre-processing is to prepare the data for analysis. Now, it may include different types of techniques like normalization, wherein we are standardizing the image intensities, which may be varied. We can do some registration to align the images coming from different modalities, or we can augment the data, right? So means expanding the data set. Why we need to do that? Because sometimes models are not going to perform on a limited scale of data, so we need some enhancing the model's ability to generalize from limited examples, you can say. Multimodal data integration techniques. Now, my approach, which I have presenting here, it actually gives you both early and late fusion techniques to integrate the multimodal data. Now, each fusion is going to treat different image modalities in separate input channels. So they are combining them early in the process, which again, if I combine them early, it's going to help in model capturing the initial correlations which are existing between the modalities. And if I do the late fusion, it's going to combine the features which are extracted from each modality into deeper layers of the model. So it's again be helpful for more complex integration. Uh, the deep learning model architecture, the third point, says that we are using a sophisticated CNN architecture basically for the multimodal data, and they are combining the different convolution layers to extract the detailed features for the imaging data. And again, we can reduce the dimensionality. We can use more dense layers to interpret the features for classification or segmentation task or detection task, whatever we are doing. Now, the figure on the right hand side, if you see here, is the first one that says the input images. Now, this input images is using, as I mentioned, the data set that is available. So it's going to start with some form of MRI images um, of the brain, which can include several types of tumors, or images as no tumor as well. Now, once these images are done, they're gonna be pre-processed, right? We need to process these images. The second one says class encoding and augmentation. Now, these images are labeled on the type of the tumor, or you can say they are into different classes, as you can see here, as pituitary, glioma, not tumor, or malignoma. So they are depending on the different classes, they are categorized. And we have different type of augmentation techniques as well, like we can do rotations, we can do flips, and transformations can be applied to increase the variability of the training data. Next comes with normalization part. Now, this normalization is basically the images are getting converted into array conversion, which means they are normalized to scale the pixel values into a uniform range, not diverse, typically between 0 and 1, right? So that we can have a consistent input to the deep learning models, which is the second in the queue. So this basically helps in overall converging the overall images during training. Now, once the images are converted into array format, uh, which is required for processing by the deep learning algorithms, it's the matrix is formed, and this is given to the deep learning model for further things. Now you can see out this small term written as here, which is transfer learning. Sorry. Yeah, is my screen visible now? So transfer learning here is the using some pre-trained models, like you can say ImageNet, which is used to extract the features from the images. And when these features are extracted from the MRI images, it will help improving the model performance by using the knowledge or gained from the different domains. You have different convolution layers here, which again perform feature extraction from the image, detect some patterns like what are the edges, what are the shapes or structures. And once these convolution layers are flattened into a single long vector, this is passed to the classification layer, which is a layer at the last to detect which is the predicted tumor. Is it the glycoma, no tumor, malignoma, or pituitary? So in the output, we get the output images, which include some visualizations like the different visualization tools. You can say heat maps or some superimposed images, which actually helps us to identify the regions wherein the actual indicates the tumor, actual part indicates the
Uh,
tumor.
Sorry,
So,
ma'am, for disturbing you. Actually, your
yeah,
screen is not visible.
okay. Is it visible now?
Yes, ma'am.
Right. So I was just talking about this figure, which is there on the right hand side. I just explained this, which is going from input images to augmentation to normalization, getting a array conversion. And then I explained all these methods which are there in the deep learning related to transfer learning, convolution layer, flatten layer, and classification layer, getting the output in the end. Now, the results which are obtained from this deep learning framework, so my model actually achieved a very high performance metrics along several key indicators which I use, such as accuracy, effort score, and other, also compared with the baseline models. So for segmentation tasks, the model again demonstrated good capability in outlining the tumor boundaries. So again, you can use different scores such as different metrics like intersection over union metrics. You can use dissimilarity coefficient to check. And when I compared this with the baseline or the single modality models, so my multimodal approach provides substantial improvements in both accuracy as well as comprehensiveness of the diagnostics. So these comparisons made highlight the effectiveness of integrating multiple modalities that I covered with some enhanced analytical capabilities of the deep learning, which I just now presented. So, what are the challenges and the future work? So, of course, we have seen a lot of challenges during this research, like data heterogeneity, like we have different imaging protocols, again, equipment along different healthcare sectors, controlled conditions. So they pose a challenge still, which we need to take care of. We need to check on the model generalization, which is working across different clinical settings and environments, and optimizing the model for real time processing, especially when we are integrating into the workflows, clinical workflows, real time workflows. So, looking forward, of course, as a research or students, you can plan to incorporate some additional imaging modalities like diffusion sensors or magnetic resonance spectroscopy instead of MRI, which will give you more insights into the tumor characteristics. We can also use some optimization for real time processing, which is actually a priority. So we aim to develop more computationally, efficient models that can operate less costly on less robust hardware as well, depending on the different clinical settings. And if we need to expand the applications to different type of other tumors, it can be scalable. So we should look ahead in those scalability factor as well. And finally, enhancing the interpretive of our model is crucial. So I have explored some models here to make the decision making process good. But again, clinicians and other people need to interpret these results. So simply generating the heat maps will not work. It needs to be visible enough for the clinicians or the non-technical background, non-technical audience background should also understand your results. So these are several challenges, or you can say future works. Overall, in conclusion, I would just comment that this research has actually developed a cutting edge deep learning framework that has given some strengths of multimodal imaging with the deep learning techniques for classification diagnosis of the tumors. And we have seen through different computational techniques how they can mark an improvement in diagnostic capabilities further for a more advanced kind of healthcare prediction outcomes. So there are some contributions to the clinical practices as well done, like the practical implications of the work of this work which I have discussed is really good because they reduce the dependency on manual diagnosis first of all, and it is enhancing the diagnostic accuracy as well, speeding up the process. Also it holds the overall potential to help the further researchers to completely change or make a new landscape for finding out some neurological diagnostics as well, because I just discussed about the brain tumors or the cancer diagnostics in predictions. Now you can scalealize this overall research to other forms of diseases like maybe Alzheimer or other neurological diseases. You can see my works, which are available on Google Scholar, and I have worked on different forms of brain tumor classifications and cancer detection techniques as well. I don't know. Again, the screen is lost, I guess. Um, yeah, so you can see some of my works on the brain tumor classification, cancer detection. I've also used few short learning and meta learning in one of the models. I've used some federated learning techniques as well, and explainable AI can also be used for having that privacy, scalability factor. Breast cancer prediction and monitoring can also integrate machine learning for decoding the complex health data. So these are some of my works on the brain tumor classification. And if you have any other questions, you are more than welcome to ask. Thank you.
Thank you so much, ma'am. If there are any questions, you may ask. Anyone? Or you may also ask in the chat box. So moving on further, our second keynote speaker, Dr. Rishabh Singh, IIT Patna, India. Dr. Rishabh Singh is a distinguished academic and research specializing in biometrics, deep learning, artificial intelligence, and computer vision. With over a decade of professional and academic expertise, Dr. Singh has made significant contribution to these fields. Before joining academia, Dr. Singh owned his expertise at Infosys Limited, where he worked for 6 years. He later transitioned into academic role at Bennett University for 2.5 years and NIT Delhi for 4 years, mentoring students and advancing cutting-edge research. Dr. Singh is author of the renowned book Animal Biometrics, Techniques and Applications, Springer 2018, and has contributed to numerous esteemed journals. His innovative work continues to drive advancements in biometrics and artificial intelligence, bridging the gap between theoretical research and practical application. I invite you, sir.
Thank you so much, Dipanshi. Am I audible properly?
Yes, sir, you are audible.
Okay. So just let me know if my screen is visible. Is my screen visible?
Yes, sir.
Okay. So thank you so much. Already Professor Surbi has covered most of the topics and related to the healthcare. I will be taking you slightly on the application orientation of the deep learning, not in terms of the what you can say the exact domain field, but how this deep learning can be used in as an application. So, before we proceed, let's say they have some traditional ML model versus deep learning model. So, in machine learning, we used to first extract the features and then we go for the classification and the output. But in deep learning, we create a model which is itself is executing, extracting some features based on the neurons or the activation functions, you can say, and it also having a classification layer at the end. So this mixture kind of thing was what you can say. This mixture kind of thing was removed, and there was a single place where the feature extraction and classification was done. Now, why this is important? This is important in machine learning. Whenever you are extracting new features and passing to the model is not retaining those informations. For example, if I am shifting from one place to another place, I want to use the same knowledge. Okay, so I cannot do that using machine learning. But think of a kid. Let's say a kid is present over here in India and he visits a computer science lab at IIT Patna, and we explain it to him. Let's say he's a 5 or 6 years old kid. We explain it to him that this is a computer science department where people are computer science. If the same kid goes to, let's say, to England or let's say Australia, any other university, and if he comes to know that okay, this is a computer science department, so he will retain that information in his computer science. That means people will be working on computers. So what I want to here is in machine learning, the feature which we had where, just give me a second. The feature we have of the memory, which we are retaining the informations. Okay, that was not exactly possible in machine learning. But in deep learning, you can gain information and you can use those information somewhere else in somewhere else applications. Because of this, of retaining the information, pre-trained models came into the picture. Pre-trained means the models who are trained somewhere else, but you are using for your own application purpose. Let's say we talk about the ImageNet dataset. So the ImageNet is actually having a huge volume of data, more than terabytes, or the data more than 1,000 classes. But in this particular case, the one which we are having, the data on which the let's say a model, let's say VGG or ResNet or Reception Net, whatever the models, when they are trained on that, we are using those models and we are using those models for our own application. So today I will show you one example where we have not retrained any deep learning model. We have just used them as a feature extractor, and that gave us a marvelous results. Because in machine learning the problem is of, you can say that the number of parameters were very less which needs to be optimized, but in case of deep learning those parameters are termed as hyperparameter. The reason is it's going to be a huge number. There are so many number of parameters which are supposed to be optimized, which we cannot do that. And it's, we can do that, but it's actually very hectic. Okay, so let's understand through this example. Over here, this machine learning, we have validation data set, training data set. We build a model and we use that model over here to transfer the knowledge. I'll come back to this picture again. But before this, I want to, the pre-trained model, which is being trained on, let's say, ImageNet, and then we are using it for our own application. When you're shifting the knowledge, we call this as a transfer learning. Transfer learning means you have learned somewhere, now you are going to a different space. Now the question arises is what to transfer, when we should transfer, and how we should transfer. So the thing is, if you see over here, let's say this is situation A and this is situation B. So what happens is if a person is, let's say, being learned on one particular area, let's say a place, he actually holds some of the features and it can be applied at task B. So if you have learned something in task A for a particular data set, same thing can be applied in a different place for task B. So if you see over here, the pre-trained models, there are very few I have mentioned. If you go over here, there to keras.io, they have listed actually, they have listed so many pre-trained models which were trained earlier. So you can use those models. We have used few, like in my work, we have used VG1619, we have used Inception ResNet, we have used residual models and all. So I'll explain you that VGG19, one of the paper which we published. So this VGG19 means there are 19 trainable layers, and there are few layers which are not trainable. For example, max pooling and all. But we are not entering into it. I just want to show you this, that VGG19 on a data set, when it was trained, that was ImageNet, it achieved an accuracy of 0.713. That is 71%, you can say. And top 5 accuracy was 90%. That means if I am just comparing one-to-one matching, it is 71. But if I am saying that, okay, if whatever I have predicted, if it is in top 5 prediction, then the accuracy reaches to 90%. So this is something for the pre-trained model. So there are lots of pre-trained models available. The advantages is it helps you to solve problems where there are constraints, like your data set is very small. You can use it over there where you have very less number of labeled data set. You cannot train a big model on a very small data set. Although there are some deep learning models who came up, let's say meta learning, where you need very small data set to train a model. But still, that meta learning again itself uses some pre-trained models. Then it becomes easy for transferring the knowledge. Suppose there is something like we see now, usually he's an experienced person, he will be having more knowledge. Okay, so that means he has gained insight from different places and he can apply those knowledge over there. So now the thing is, this transfer learning, when we are talking about, we are saying that we have a data set which is very huge. Let's train some models. Once it has learned, now I will be utilizing, or you can say exploiting, the learning of that particular model. And it actually push you towards the generalization intelligence. That means the drawback which we had in machine learning, it is specific to a data set that we are trying to remove, and that we are trying to say that, okay, it's a generalized model. Let's talk about this paper which we published in the year 2020. It's about a breast cancer classification. Now, the first major problem in this breast cancer classification was there are two classes, cancers and non-cancers. The one which we were having, there were 1,75,000, I guess. The one of the classes has the data, and the other class has just 80,000 or 70,000. So it was highly imbalanced. So if you go with machine learning and try to work on a highly imbalanced data set, either first you'll have to use some pre-processing methods like smart tumbling or something, so you can undersampling or oversampling, so that the number of samples could be similar in both the places. But we don't want to do that. We don't want to do that. We just want to see that, okay, the number of classes which we have, there are two classes in which the number of images are different. Still, this through transfer learning we can overcome. Now, if you see over here, this is actually a architecture of VGG90. So over here you have block 1 where there are two learnable layers, CNN layers, and this was the max pool. Same way, there are two learnable and one max pool. There are 4 and one max pool, like that. So you have total 16 trainable layers. The last layer which you are seeing, that is about the max pooling, which does not have any parameter. Now, this 16 layers and this 3 layers are fully connected layers. So when you send the data, when the data is being sent, when it gets the prediction, then you actually calculate a loss, then you back propagate and update the weights. We did nothing sort of this. A model, this entire thing, this section was actually trained on some ImageNet data set. What we did, we just removed this particular section. We just deleted this particular section. In this particular scene, when we deleted this, we just extracted the features from different layers. That means When you talk about the block 1, I extracted the features, because when I'm sending this image, if you look at this image, not as a one, but you look at it as a pixel. And when I'm saying pixel, you try to look at it as something as RGB, red, green, and blue. Okay, so you have RGB values present in an image. So when I'm saying I want to go with this particular layer, let's say block 1, I'm sending those values over here. Okay, you can just imagine the CNN. It's working on large matrix. We extracted some features. Now, this initial layers, okay, these initial layers, let me just explain you in a different way. Just give me a second. Just actually, I didn't connect my writing pad. I'll just connect that. So you see over here, when I'm talking about this particular block, okay, let's say I'm talking about block 1, layer 1. So what it does is, this block will give me generalized features. Now, what does the generalized feature means? Suppose you have a face of a person, it will just give me some edges, some random edges, okay, of the entire face, like this eyebrow it might give you, this line it might give you. So the each CNN will try to give you some edges. So initial layers which gives you the edges, they are randomized edges. The last, as in when you try to proceed over here, these edges will start forming a shape. Then you further go, once you reach the end, it will actually form a shape of a person, something like this. Okay, it will form a shape of a person by combining those edges. So initial blocks will give you edges, a generalized edges. The last layer will give you edges specific to your data set. Now, why specific to the data set? Because I will be using those edges for the purpose of, let's say, classification I'm talking about. So what we did is, we did not train anything. We did not train anything. This last layer even, we did not train. We just removed all the fully connected layers, everything, loss function, everything. We don't use anything. What we said, okay, you first layer, you take the features, last layer, you take the features. Similarly, from each layer, you take a feature. You take a feature from each layer and send it to a machine learning model, a simple machine learning model. So suppose first image goes, we know that it belongs to IDC 0. Whatever feature it gives, I will be sending to the cluster. So from each layer of each block, I extracted some features and I trained my model. The best part which we see over here is block 1, con 1, if I'm talking about. There were 1,60,000 features which got generated. 1,60,000. Same way, if you talk about block 5 pool, there are 512 features which got generated. So first thing is, I said the initial layers will give you the generalized edges. The last layer will be specific to your data. And the second thing is, when I'm moving towards the end, the number of features is started reducing, the number of features. So what we did is, these features which we extracted, we built a ML model on top of this, on each one of them, machine learning model. And we predicted. So you see over here, after doing the prediction, we achieved some accuracy, and you see the retraining with VGG19 gave 0.90. With this it was 0.82. With random forest, you see over here we got 7868. Okay, in this means that only the last 3 layers we have retrained. This means that we have retrained the entire model. Okay, but over here, this VGG19 plus random forest, the one which you see, although the accuracy is less, slightly less, but the thing is, your computational cost has decreased. I'm not training the model. I am not building the model from the scratch. Neither I am defining any hyperparameters, nor I am fine tuning any hyperparameters. I am just proceeding. Okay, so I'm just going forward and I'm just trying to see that, okay, how many, what is the accuracy that I can achieve with very less computational power. So there are some applications where if there's slight accuracy, there's a slight difference in the accuracy, it is acceptable. So that's what we did over here, and we got actually very good results. If you have any queries, any questions, you can stop me at any point of time. We can discuss that and then we can proceed further. Let's proceed. So the one which I was explaining you is just, I was saying, I have not trained any model. I have just reused the model which I had in my hand. Now, there's another application. This is actually a transfer learning, a pure reuse them for extracting the feature for my data set. There is another thing which what you can say, there's something as federated learning which was there. Like I said, it is for generalization purpose. Now generalization can happen when you are actually retaining some of the information and you're also having access to most of the data sets. Or when I'm saying this is a generalized rule, that means this rule will be applicable to all the data sets which we have in a hand. But the problem with the medical field is nobody is ready to share their data set with anybody else. Let's say I'm a hospital, there's another hospital B. Hospital A will never share the data with hospital B. Faculty will go, the students will go, or let's say the patients will go. Every time the new registration process will happen, every time the new test will be performed, every time they will be just holding the data. So this federated learning, when it came, it said that, okay, you keep your data with yourself. Only thing is, we will train the model on your data set. We will never share the data. We will share the trained model with someone else. Or the features, when it is being trained, the parameters after training of the model, we will be sharing it with someone else. So if you look over here, this is federated learning. There is some database as DB1, this is DB2, this is DB3, this is DB4. You just think as this is, let's say this is hospital 1, this is hospital 2, this is hospital 3, and this is hospital 4. So what it says is you just learn, you build some model on top of this databases individually. Don't mix them. So the thing is, once you have reached over here, there are 4 learning models. Now the question is how we can combine the learning models. I'm not combining the data. I'm just combining the models. So we will be having a single learning system with us. We'll have this learning system. Now, this learning system, when I say, when instead of this, I will be replacing it actually over here. That means individually you have learned, individually all the hospitals, they have created a model, they have learned. Now you have combined them. Okay. So that in future, if a new hospital is coming up with a new database, he doesn't have to create another thing. They can use this generalized model. So what usually people do is there are different ways to do it. One of the way was you should have a generalized learning system. Okay, you create a model with some parameters. You send that to each of the hospital. Okay, you have sent the model with some parameters. Now later on, they will train themselves on this, and once they have trained, they will send the parameters back to the centralized server. The centralized server will combine those parameters. Let's say there's something as fed average, where they will be doing the average and then finally proceeding further. So what I'm trying to say is there is a single model which we have. Let me call it as a master. I have sent that to all the hospitals. They have trained on that particular set, their data set, and they have sent it back, the model itself. And you are now averaging the model. Same way, once it has the average has been done, now we will be sending it back after doing the average. That means this, and this model will be same. There's no difference in that. Each one of them will have the same information, same number of layers, same number of parameters, same number of optimization parameters. Everything will be same. So what can they do is now they will start testing this. Okay, and if they find that okay, there is some issue that has to be retrained again, they will again send the model back to the central server. It will retrain, do the average, and send it back. So this is a basic federated learning, but there is a problem with this. Over here, you are having three places, servers, where on which you are training your data. Again, you have a centralized server. So I don't want my centralized server to be present or something. I don't want to have that. Second thing is when I'm sending the informations, there may be a model. There may be a model which might be poisoned. So this entire model will be poisoned. Okay, poisoned has been that is has instead of learning on good parameters, it has learned on misclassification most of the things. So if you see, the benefits of this federated learning is there is no data sharing. That means I'm not sharing my data with anybody else. And second thing is I'm not sending this database over here. The model will be hardly in MBs, the architecture and the weights. But this data set might be in GB or might be in terabytes, anything. Okay. So I won't be sending this to them. And the only thing is over here, the network traffic will be reduced if you are using it. Now I am seeing about network traffic. See, internet is something in, let's say over here, it's one of the highly unreliable resource. We don't know when the traffic is going to increase, when the traffic is going to reduce, when the network is going to fail. We don't know. So it is one of the highly unreliable resource. And on that, if you are sending GBs or terabytes of data, it still becomes very heavy. So it's better that we just shift the model and its parameter. So there are two benefits for which the federated learning was achieved. The one of the work which we did earlier was we had, let's say, 1, 2, 3, 4. There are 4 clients we have. They have their own databases over there. Let's say data 1, D2, D3, Dn. They have their individual databases. What we did is initially we gave some random inputs. We gave some random inputs and we send it over here to the B database. Okay, some noise you can say over there. Once they have learned on this, we shared the logits. We never shared the models. Instead of sharing the model, we just share the logits just at the last layer before sending it to the softmax and all. So the logits, we retransmitted it back. We retransmitted it back, and this average of logits we did over there. If you're seeing over here, this entire client, if I look at the initially, this is dk and b. I'm training my model on this data sets, these two data set. I'm doing the classification. This edge side log it, I'm sending it back for the average. So this of each layer will be combined and then it will be sent back over. So that after this, when we are going for the cost function, okay, let it be anything, let's say the cross entropy or something. Now we are combining that. So this average will be, it will help you while back propagating for each one of them, it will actually help you to improve. And we got very good results. So over here, neither we shared the data, nor we shared the model, neither we shared the weights. We just shared the logits during the training time, and using which we got this model over here. So when I'm talking about, let's say, transfer learning, whenever I'm talking about, let's say, federated learning or meta learning, everywhere the models which you have, those models are actually most of the time, I'm not saying every time, most of the time, they are from a pre-trained model. Like I said, the initial phase, pre-trained means you have an architecture defined, you have the weights. If you want, you update the weights, but in our case, we never updated the weights. We just use as it is. So this is all we have. If you have any queries, any questions, you can ask me. There are two things which we have discussed in now. Guys, if you have any queries or any questions. See, whenever we go with the deep learning thing, the main objective is not to create your own model. Main objective is to get a generalized model. Most of the time you will find that the people are just using database data on which they are training. They are in just gigabytes. But the thing is, if you look at the data set on which these models are being trained, they are in petabytes, yottabytes, and zettabytes. So on less amount of data, how you can retrain it with very few samples? That's the biggest challenge right now. Okay. Yeah. If there's any questions.
Are there any questions anyone want to ask? You may also ask in the chat box. Thank you so much, sir, for those wonderful words. Now I invite Dr. Ankit Vidyarthi, JUIT, joint convener for the vote of thanks.
Am I audible?
Yes, sir.
Okay. Thank you, everyone. First of all, I would like to thank the DuyTan University Vietnam for organizing this event, being a partner of our conference, and special thanks to Deepak sir for giving us all of us the opportunity to handle the respective roles to each and everyone. And special thanks to our keynote speakers. First, Dr. Surbhi Bhatia Khan for giving her talk on brain tumors and the deep insights, how we can analyze the respective deep learning models, and Dr. Rishabh to give the very detailed explanation on how we can handle these medical images using these deep learning and the machine learning models. So that was a great insights of these application areas and the domain of medical imaging. Thank you, Dr. Rishabh and Dr. Surbhi, for giving your valuable time to this conference. At the last, we have some respective session chairs who have given their consents timely and organizing all the sessions very smoothly. So special thanks to all the session chairs who have handled our conference sessions. So we are really very thankful towards them. And since every conference has some backends, back roles, special thanks to all the authors who has shown their interest towards ICCRDA to accept this conference as their publications to their respective papers. So really, thanks to all the co-authors, the reviewers, backend supports, student volunteers who are giving their times to handle all these sessions. So in short, thank you everyone for making this conference a successful event. And in the meantime, in the next year, we will again try to communicate with you all and would like to see your participation again in the next version of ICCRDA. Thank you everyone. Thank you.
Thank you so much, sir. Now with this, our session has been concluded. Thank you everyone for joining. Please turn on your cameras for the group photograph. I request everyone to turn on their cameras for a group photograph. Please turn on your cameras.
Excuse me, ma'am, there is no permission to turn on the
It
camera.
has been disabled. You please enable it.
Beneath,
You can check now.
Yeah, it's working fine now.
thank you everyone for joining.